Hello. Now, welcome back here. This is Data Analysis 2, the second part, so it's in the second semester. Let's continue with the topics which we have. And actually, you see, this time we should have a Zoom class as well. But before starting with the new topic, let's also summarize or think about it what we just learned in the latest class. So communicating data was the class, and now we continue with how to tell if your toaster is learning. Machine learning, so the basics of machine learning. Finally, we start with that which actually was our goal within 2 semesters. So before that, again, let's look at it, what we just learned. So first of all, we started with the advanced probability, chapter 6. Then we continued with basic statistics, so advanced probabilities. We talked about Bayesian ideas, Bayesian theory. Then what are statistics we learned and how to obtain and sample data. And then we continued with advanced statistics, so sampling distribution, point estimates, and we also made hypothesis test, so the chi-square, as I remember, right? So yeah, chi-square goodness of fit test, and example of chi-square test for goodness of fit, and the chi-square test for association and independence. So that was up to chapter 8. Now communicating data was chapter 9, and it matters, right, how we communicate and what we communicate, and again, if we can identify effective and ineffective visualization. Now, what we learned here are scatter plots. So scatter plots, what are scatter plots again? So a scatter plot is has the main goal of a scatter to highlight relationship between 2 variables and reveal a correlation. Now it's about quantitative access, so no qualitative data here is allowed. Now line graph is uses quantitative variables and is also very often used. And the next one, what we learned, is bar chart. So we generally turn to bar charts when we try to compare variables across different groups. So the x-axis is generally a categorical variable, while the y-axis is the quantitative. So we mix the categorical variable with the quantitative variable to get the bar charts. Then histograms actually show the frequency distribution of a single quantitative variable by splitting up data by range into equidistant bins and plotting the row count of observation in each bin. This is what we learned, and we remember that there is no space in between normally. And then we learned also what are box plots, the minimum value it covers, then the first quartile and the median and the third quartile and the maximum value. We plotted them, and we also learned about them when actually statistics may lie. Indeed, not statistics, but graphs could be misused or wrongly used, and that's why we call it like when graphs actually lie. Then we learned about correlation versus causation. Then the Simpson paradox is a formal reason for why we need to take confounding variables seriously. The paradox namely says that a correlation between two variables can be completely reversed when we take different factors into account. This means that even if a graph might show a positive correlation, these variables can become anti-correlated when another factor is taken into consideration. So that is the Simpson paradox. And if correlation doesn't imply causation, then what does? So we continued with verbal communication about our data, and here it comes to the major strategy, that is the why, how, and what to present. So tell your audience why you present something, then how you prepared the problem, and how you do data mining, data cleansing, hypothesis testing, and so on and so on. And then finally, what the outcome is, so what we can learn from that, what you did. Now, here we come, as I said, to machine learning this time. And let's see. What is actually machine learning? This is a very, very huge topic. So it's chapter 10 is really long. Just to mention here, I think we have like over 60 slides to go through. Lots of codes. So please make sure that you are on the topic and you also do the programming part. Okay, now, so types of machine learning, so supervised and unsupervised, linear regression, then logistic regression, probability odds, and log odds, and then we go through the dummy variables, and then we finish after that. So machine learning is really famous these days, right? It seems that every single time we can hear about this machine learning, whenever we talk about startups or news and hear something about revolutionary piece of machine learning technology and how it will change the way our life. So in this chapter, we start to talk about machine learning, the basics, and we define the different types of machine learnings along with some samples, and then we talk about the regression classification and even more. Then we will reveal what machine learning is and how it is used in data science, and a difference between machine learning and statistical modeling, and how machine learning is a broader category of that statistical modeling. So our goal is actually to utilize statistics we learned until now, probability we learned until now, and algorithms thinking as well, in order to understand and apply essential machine learning skills to practical industries, to practical examples, like in the case of marketing. Examples will help us to see and to predict the stars rating of restaurants through the reviews, predict some kind of disease in the future, predict heart attack in the future, spam email detection, and much more as well. This chapter focuses more on machine learning as a whole and a single statistical model. The subsequent chapters will also go deeper and we will even have the chance to learn more complex issues. Yet, I'm not sure if we can continue from after chapter 10, but let's see that part. Okay, so all right, now what is actually machine learning? Well, in chapter 1, how to sound like a data scientist, we actually defined machine learning as giving a computer the ability to learn from data without being given explicit instructions or rules by a programmer. This definition is still true. Machine learning is actually about the ability to ascertain certain patterns, so signals out of a data, even if the data has inherent errors in that, so basically noise. Machine learning models are indeed able to learn from data without the explicit help of a human. That is the main difference between machine learning models and classical algorithms. Now, classical algorithms, okay, we are not that there. So, classical algorithms are told how to find the best answer in a complex system, and the algorithm then searches for these best solutions and often works faster and more efficient than a human. Well, but there is a bottleneck here, and that's the human. So the human has to come up with the best solution first. In machine learning, the model is not told the best solution, and instead is given several examples of the problem and is told, figure out the best solution. Now, machine learning is just another tool in a tool belt or the toolbox of data scientists. It is on the same level as statistical tests, so like chi-square or t-tests, or uses Bayes probability statistics to estimate population parameters. Now, machine learning is often regarded as the only thing data scientists know how to do, and this is a simple stupidity. So, a true data scientist is able to recognize when machine learning is applicable and, more importantly, when it's not. Machine learning is a game of correlations and relationships. Most machine learning algorithms in existence are concerned with findings and or exploiting relationships between data sets. Now, data sets are often represented in Python as pandas data frame. Once machine learning algorithms can pinpoint on certain correlations, the model can either use these relationships to predict future observations or generalize the data to reveal interesting patterns. Well, a great way to explain machine learning is to offer an example of a problem together with two possible solutions. One, using a machine learning algorithm, and then the other, utilizing a non-machine learning algorithm. So, example is facial recognition, as you see here. Say this problem, so by itself, is well documented, as you see here. Given a picture of face whose face doesn't does it belong to? Suppose you wish to implement a home security system that recognizes who is entering your house. Most likely during the day, your house will be empty most of the time, and the facial recognition must kick in only if there is a person in the shot. This is exactly the question I propose we try and solve. Given a photo, is there a face on it? So, now turn back. So let's see the two solutions. The non-machine learning algorithm that will define a face as having roundish structure, 2 eyes, hair, nose, and so on. The algorithm that looks for these hard-coded features, so these are hard-coded and it's not soft-coded in a photo, and returns whether or not it was able to find any of these features. The machine learning will work differently. The model will only be given several pictures of faces and not faces that are labeled as such. So from the examples, let's call training sets, it would figure out by its own definition, actually. So here it is. The machine learning version of the solution is never told what a face is. It is merely given several examples, some with faces and some without. It is then up to the machine learning model to figure out the difference between the two. Once it figures out the difference between two, it uses this information to take in a picture and predict whether or not there is a face in the new photo, in the new picture. So for example, to train the model, we will give the following 3 images together with the face, and no face titles. The model will then figure out the difference between the pictures labeled as face and the images labeled as no face, and be able to use the difference to find the faces in the future pictures. As we know, machine learning isn't perfect. Not yet. We are not that so far. So there are many problems around machine learning. Many are specific to different models being implemented, but there are also some assumptions that are universal for most of the machine learning models. Well, first of all, the data used for the most part is processed and cleaned using the methods outlined or we talked about actually during the earlier chapters. And almost no machine learning model will tolerate dirty data with missing values or categorical values. So at that point, we have to talk about dummy variables, which we fill up, and then we can drop them again later on to avoid the mistakes or miscalculations of the models. Each row of a cleaned dataset represents a single observation of the environment we are trying to model. If our goal is to find relationships between variables, then there is an assumption that there is some kind of relationship between these variables. This assumption is actually really important. Many machine learning models take this assumption really seriously. These models are not able to communicate that there might be a relationship. Now, machine learning models are generally considered as semi-automatic, which means that intelligent decisions by humans are still necessary. The machine is very smart, but has a hard time putting things into context. The output of most models is a series of numbers and metrics attempting to quantify how well the model did. It is up to a human to put these metrics into perspective and communicate the results to an audience. And now, most machine learning models are also sensitive to noisy data. This means that the models get confused easily when you include data that doesn't make any sense. So for example, if you are attempting to find relationships between economic data around the world and one of your columns is puppy adoption rates in a capital city, the information is likely not to be relevant and will just confuse the entire model. These assumptions will come up again and again when dealing with machine learning. They are all too important and often ignored by novice data scientists as well. How does actually machine learning work? Each flavor of machine learning and individual model works in very different ways, exploiting different parts of mathematics and data science. Yet, in general, machine learning works by taking in data, finding relationships within the data, and then giving as output what the model learned, as illustrated here also by this diagram. Now, we can explore different types of machine learning models, and we will see how they manipulate data differently and come up with different outputs for different applications. Let's talk about the types of machine learning. So, well, again, back to chapter 1, right? We talked about statistical and probabilistic models. These models utilize statistics and probability, which we also then went through during the previous chapters, in order to find relationships between data and make predictions. This time, we will talk about the following. Types of data, organic structures they utilize, so tree, graph, neural network, the field of mathematics that are used here, so statistical and probabilistic, and the level of computation required to train, that is the deep learning. So only for the purpose of education, let's see a simple breakdown of machine learning models. So supervised learning, unsupervised learning, and reinforcement learning. Now, supervised learning finds associations between features of a dataset and the target variable. Indeed, supervised learning models might try to find the association between a person's health features, health characters, heart rate, obesity level, and so forth, and then that person's risk of having a heart attack in the future. These associations allow supervised models to make predictions based on the past examples. This is often the first thing that comes to people's mind when they hear about machine learning, but there's no way it does encompass the realm of machine learning. Supervised learning models are often called predictive analytics models. The name shows also the ability to predict the future based on the past. Now, also supervised machine learning requires a certain type of data called labeled data. This means we must teach our models by giving its historical examples that are labeled with the correct answers. Recall that, for example, the facial recognition example just we had before. That is a supervised learning model because we are training our model with the previous pictures labeled as the face or not face, and then asking the model to predict whether or not a new picture has a face on it or not. Specifically, supervised learning works using parts of the data to predict another part. So first, we must separate the data into two parts. That is the predictors, which are the columns that will be used to make our prediction. And these are sometimes called as features, inputs, variables, and independent variables. And the response, which is the column that we wish to predict. This is sometimes called the outcome, the label, the target, and the dependent variable itself. So independent are predictors, dependent are depending on the predictors, so that's why we call them dependent variables. Also, supervised learning attempts to find a relationship between the predictors and the response in order to make the prediction. The idea is that in the future, a data observation will present itself and we will only know the predictors. The model will then have to use the predictors to make an accurate prediction of the response value. Its example, well, the use of scooters in Seoul streets, or another example is given by heart attack prediction, as our book also shows. Well, suppose we wish to predict if someone will have a heart attack within a year. To predict this, we are given the person's cholesterol level, blood pressure, height, the smoking habits, and also perhaps more about blood. Yeah. So blood data. From this data, we must actually ascertain the likelihood of a heart attack. We must find it out. How the likelihood is, how high the likelihood is. Suppose to make this prediction, we look at the previous patients and their medical history. As these are previous patients, we know not only the predictors, but we also know if they actually had a heart attack. Now, this is a supervised machine learning problem because we are making a prediction about someone using historical training data to find relationships between medical variables and heart attacks. So here you see data, predictor and response, the cholesterol, blood pressure, heat, smokes, and then will it have a heart attack within a year? And the supervised machine learning will recognize the relationship between predictors and response. Well, we hope that we will know a patient that patient will walk in tomorrow, and our model will be able to identify whether or not this patient is at risk for a heart attack based on his conditions, and just like a doctor would actually. As the model sees more and more labeled data, it adjusts itself in order to match the correct labels given to us. We can use different metrics, explained later in this chapter also, to pinpoint exactly how well our supervised machine learning model is doing, right? And how it can better adjust itself. One of the biggest drawbacks, setbacks, or disadvantages of supervised machine learning is that we need this labeled data, so we need the historical data, which can be very difficult to get. Suppose we wish to predict heart attacks. we can need actually thousands of patients' data along with their field medical information and years worth of follow-up records for each person. Well, it's easy. No, it's not. It's really difficult to get them. In short, supervised model use historical labeled data in order to make predictions about the future. Some possible applications for supervised prediction, supervised learning include also stock price prediction, weather prediction, and crime prediction. Well, you can see here how each of the predicting examples use the word prediction, which makes sense, seeing how we emphasized supervised learning's ability to make predictions about the future. Predictions are not where the story actually ends. Here is a visualization of how supervised models use labeled data to fit themselves and prepare themselves to make predictions. Here we go. Yeah. Now you can see how the supervised model learns from a bunch of training data, and then when it's ready, it looks at on-scene cases and outputs a certain prediction. It's not only about predictions, so supervised learning exploits the relationship between the predictions or predictors and the response to make predictions, but sometimes it is enough just knowing that there is a relationship between them. Suppose we are using a supervised machine learning model to predict whether or not the customer will purchase a given item. Possible data set would look like this: person ID 1 and 2, age 63 and 24, and female, male, and employed, no, and yes, and then both, something yes, no. And then note that in this case, our predictors are age, gender, and employed, while our response is both or not. So yes, we would like to see if somebody buys the products or not. Now, assume that the model is trained on this data and can make really good predictions about whether or not someone will buy something. That is, in and of itself, it is exciting, but there's something else that is arguably even more exciting. The fact that we could make accurate predictions implies that there is a relationship between these variables, which means that to know if someone will buy your product, you only need to know their age, gender, and employment status. This might contradict the previous market research indicating that much more must be known about potential customer to make such a prediction. This speaks to supervised machine learning's ability to understand which predictors affect the response and how they do that. So for example, are women more likely to buy the product? Which age groups are prone to decline the product? And is that a combination of age and gender that is a better predictor than any single column on its own? As someone's age increases, do their chances of buying the product go up or down or stay at the same level? So it is also possible that all the columns are not necessary. A possible outcome or output of the machine learning might suggest that only certain columns are necessary to make the prediction, and that other columns are only noise, so not related to our issue, our question. Now, types of supervised learning, we can see here. Two types. So, regression and classification. The difference between the two is quite simple and lies in the response variable. Regression. Regression models attempt to predict a continuous response. This means that the response can take on a range of infinite values. Consider the following examples. For example, dollar amount, salary, budget, temperature, time, so generally recorded in seconds or minutes. Classification attempts to predict a categorical response, which means that the response only has a finite amount of choices. Examples include the ones like here, cancer grade 1, 2, 3, 4, 5, true and false questions such as the following: will this person have a heart attack within a year? Will you get this job? Given a photo or of a face, who does this photo of face belong to? So facial recognition. And predict the year someone was born. So note that there are many possible answers, over 100, but still finitely many more. So let's see an example for regression. The following graph show a relationship between three categorical variables: age, year they were born, and education level, and the person's wage. Well, you can note here that even though each predictor is categorical, this example is regressive because the y-axis, our dependent variable, our response is continuous. Our earlier heart attack example is classification because the response was, will this person have a heart attack within a year? So we have two answers, yes or no. Now, data is in the eyes of the beholder as the next topic. Well, sometimes it can be tricky to decide whether or not you should use classification or regression. Consider that we are interested in the weather outside. We could ask the question, how hot is it outside? In which case your answer is on a continuous scale, and some people answer 60.7 degree or like that. So 31 degrees, 37 degrees, 31.2 degree. However, as an exercise, you could go and ask 10 people what the temperature is outside, and you will see that some of them will not answer in some exact degrees, but will just answer like it was a year ago, or like it was in several years ago, right? And then we might wish to consider this problem as a classification problem, where the response variable is no longer an exact degrees, but it's in some kind of bowl or bucket. That would only fit or be a finite number of buckets in theory, making the model perhaps learn the difference between 2000s and 2010s and 2020s. And the second type of machine learning is the unsupervised learning that doesn't deal with prediction but has a much more open objective. Unsupervised learning takes in a set of predictors and utilizes relationship between the predictors and in order to accomplish tasks such as the following. So once again, unsupervised learning takes in a set of predictors and utilizes relationships between the predictors in order to accomplish tasks such as the following. It reduces the dimension of the data by condensing variables together. An example could be simply just given by file compression. Compression works by utilizing patterns in the data and representing the data in a smaller format, then finding groups of observation that behave similarly and groups them together. First element on this list is called dimension reduction, and the second is clustering. So dimension reduction is the compression of a file, and clustering is finding the groups. Both of these are examples of unsupervised learning because they do not attempt to find a relationship between predictors and a specific response, and therefore are not used to make predictions of any kind. Unsupervised models instead are utilized to find organizations and representations of the data that were previously unknown. The predicting screenshot is a cluster analysis. Do we have it here? No. Okay. So a big advantage of unsupervised learning is that it does not recognize labeled data, which means that it is much easier to get data that complies with unsupervised learning models. Of course, a drawback to this is that we lose our predictive power because the responsive variable holds the information to make predictions, and without it, our model will be hopeless in making any sort of prediction. A big drawback, disadvantage, is that it is difficult to see how well we are doing actually. So where we are. In a regression or classification problem, we can easily tell how well our model predicts, right? By comparing our model answers to the actual answers. For example, if our supervised model predicts rain and it is sunny outside, the model was incorrect. Then if our supervised model predicts the price will go up by $1 and it goes up by 99 cents, our model is very, very close. In supervised modeling, this concept is foreign because we have no answer to compare our model to. Unsupervised models are merely suggesting differences and similarities, which then requires human interpretation. So in short, the main goal of unsupervised models is to find similarities and differences between data observations. We will then go later deeper in this topic. And the last one is the reinforcement learning. In reinforcement learning, algorithms get to choose an action in an environment and then are rewarded positively or negatively for choosing this action. The algorithm then adjusts itself and modifies its strategy in order to accomplish some goal, which again leads to more rewards. Now, this type of machine learning is very popular in artificial intelligence, so AI assisted gameplay, as agents are allowed to explore a virtual world and collect rewards and learn the best navigation techniques. This model is really popular in robotics, especially in the field of self-automated machinery, so self-driving cars. So what we know here is self-driving cars read in sensor input, act accordingly, and are then rewarded for taking a certain action or not taking a certain action. It can be also thought that reinforcement is similar to supervised learning in that the agent is learning from its past actions to make better moves in the future. However, the main difference lies in the reward system. The reward doesn't have to be tied in any way to a correct or incorrect decision. The reward simply encourages or discourages to take action or different actions. Reinforcement learning is at least the least explored of the three machine learning types, and therefore it is not explored in a great length here, and we cannot go furthermore with that. Let's take an overview of the types of machine learning. So the three types again: machine learning, we see here supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, we talk about regression and classification. And in unsupervised learning, clustering and dimension reduction. Just remember the two examples. And then agent and state-based learning. So reward-based learning. Now, each of the three types of the machine learning has its benefits and its disadvantages. Supervised learning. This exploits relationships between predictors and response variables to make predictions of future data observations. The pros, so advantages, it can make future predictions. It can quantify relationships between predictors and responsive variables. It can show us how variables affect each other and by how much
And the con itself is it requires labeled data, so data from the past, which might be very difficult to get. So historical data is required. Unsupervised learning, unsupervised machine learning, this finds similarities and differences between data points. Here again, pros, it can find groups of data points that behave similarly that a human would never have noted or noticed. It can be a pre-processing step for supervised learning, and you can think about the clustering of a bunch of data and then using these clusters as response. And then it can use unlabeled data as well, which is much easier to find. But it has zero predictive power. It can be hard to determine if we are on the right track. It relies much more on human interpretation. Unsupervised, and reinforcement learning is the next one. So this is reinforcement learning is the last one which we mentioned here. This is reward-based learning, reward-based machine learning that encourages the agents to take particular actions in their environment. The pros are very complicated reward systems create very complicated AI systems. It can learn in almost any environment, including the Earth as well. The disadvantages that that should be taken into account are the following. The agent is erratic at first and makes many terrible choices before realizing that these choices have negative rewards. For example, a car might crash into a wall and not know that is not okay until the environment negatively rewards it. It can take a while before the agent avoids decisions altogether. And agents might play safe and only choose one action and be too afraid to try anything else for fear of being punished. So an agent might be afraid of getting punishment if they do some kind of action or do not do some kind of action. Alright, so here it is the next one. How does statistical modeling fit into all of this? Well, up until now, we've been using the term machine learning, but you may ask how statistical modeling plays a role in all of this. Well, this is a debate topic also by the data science. I believe that statistical modeling is another term for machine learning models that heavily relies on using mathematical rules borrowed from probability and statistics to create relationships between data variables, often in a predictive sense. Now, we can continue our work with statistical or probabilistic model, linear regression. That's it. So let's stop here for a moment, because I believe that this is time to stop here. From here we will have many more assignments. You see that here. So once again, what we learned about are the types of machine learning, what machine learning is. We differentiate between supervised learning, unsupervised learning, and reinforcement learning, so the agents. And that is the relation to AI
as well here. I would say thank you very much for your attention, and we can continue with, as I said, linear regression now. Thank you. Goodbye.